Yeah, what's up, people? It's Robert Basano. Let me do a few housekeeping clean things here right now. And I don't know who's watching, but we do a few things here, people, to kind of clean up a little bit. And we'll just do the share screen real quick for you guys, just so that people can have something to look at. Just stand by here for a second. Just stand by. Just give me a sec, people. Chat among yourselves right now. Just let me get All right, people. So here's what we're gonna do. Let me do a share screen with you guys. I'm not gonna take long with this. Just to let all you know, it's not gonna be a long one. So let me see who's out there. Okay. So we're gonna call the speak to Noah. Okay, that's who we're gonna speak to. Let's see who the team members are first. All right, we got several team members here. We got Suzanne Hilding. She probably won't be available, but what we're gonna do is we're gonna put her name in the database. Okay, we're gonna put her name in, and then we're gonna pick and choose to see who we can call here. So here's the staff directory. We're going to go to the public version. Put her name in there. Let's see what we can see. Okay, Susan Hilton. All right, Susan. There's her telephone number. Office of Projects and Partnerships. You think she'd know the answer? Let's see if, let's call her up. Let's call her up and stand by here for a second. Let's do some things. Yeah, why not? Let's call her ass up. So let's do it. Actually, let me do this for a second here. Let me do this. And any of you fucking weirdos out there, with all due respect, don't be fucking calling the numbers that you see on this fucking screen. You understand me? For any of you weird, psychotic people decide you want to call the phone numbers of people who you see on my Skype list, I'm going to tell you here right now, you're going to make a really fucking big mistake, because then I'll have your fucking phone number. So let's do this. Let's call up Susan. Let's see. 713-0100. Let's see. Let's see if Susan's home. Director Suzanne Hilding.
Thank you for calling Office of Project Planning and Analysis. This is Erica speaking.
Erica, how you doing? Is Director Hilding available?
She's actually in a meeting right now.
Oh, is she in the meeting with the Discovr team?
No, she is not. I'm sorry. Can I ask who's calling?
Yeah, my name is Robert Bassano. I'm a graduate student. I'm studying applied physics. I was wondering if any one of the Discovr team members are available. Maybe Harry Whiteley, or Jim Silva, or Richard Ullman.
Let me see. So that's
out.
I can transfer you over to Rich if you like.
Richard Ullman.
Yeah.
Yeah. Transfer me to Richard, please.
Okay, give me 1 second.
I appreciate that. Thank you.
You're welcome.
This is Rich Ullman.
Mr. Ullman, how are you? Robert Bassano.
Hi, Robert.
How you doing? So listen, it's interesting because they transferred me to you. You're the deputy chief for systems engineering for Discovr?
No, but
no. I'm sorry.
I'm deputy of the Program Management Execution Division, and Discovr is within our division. But what do you need about Discovr?
Oh, okay. I just want to ask a few questions. I see that you got your MS in systems engineering at John Hopkins. I start there. Yeah, I start there in the fall.
Well, good.
Yeah, I start there in the fall. I'm also simultaneously pursuing a master's in applied physics at Columbia too. So this fall, so I'll start there as well. So
Wow.
what I wanted to, I'm sorry.
And what's your role now with Discovr?
No, I'm not doing anything with Discovr. I'm a graduate student.
I
got really interested in picking a particular concentration, and looking into fluid dynamics, and a lot of the research that I'm working on brought me in this direction with regard to heliophysics. So the questions I wanted to ask regarding Discovr actually involve some of the technical specs on what type of what, because I looked at the general information that's available for Discovr already. Okay.
Yeah.
So what I wanted to know is there's no information available saying what type of, say, temperature sensors are actually on Discovr.
I see. It's not a temperature. Well, I don't know exactly what you're going at.
Okay.
But the particulars of the spacecraft design in terms of the sensors about the health and safety of the spacecraft. Is that what you're talking about?
No, specifically, like, I'll give you an example. I'm on you guys' website right now, and it shows Discovr, shows the magnetometer, the Faraday cup, the NiStar, Epic,
right,
which is the camera that's basically recording everything. Then we got the propulsion system and solar array. Now, Discovr is at the Lagrange point. This is an area, that I'm understanding where you guys already identified. Discovr will stay stationary in that particular orbit around the sun. Is that?
It's not exactly true, but close
okay
enough.
Now it's orbiting around. Is it using its propulsion system or just basic inertial orbital mechanics science?
It orbits around the stationary the Lagrange point itself.
Okay.
What's called a Lissajous orbit, and it does require station keeping from time to time.
Okay. So.
But not. Go ahead.
No. Go ahead. I'm listening.
So it does have the ability. It's got thrusters and it can do station keeping.
Okay.
In order to keep the orbit, it stays from our vantage point a few degrees off of the sun, which is important to us because when you look at the sun, not only in the light spectrum but in the electromagnetic spectrum, it's blinding. And so really, if it were straight on at the sun, it would be very difficult for us to receive the signal.
Okay.
So it's generally a few degrees off the sun.
Now,
which allows us to get that signal.
Now, what do you know much about Soho? Soho's out there as well, right?
That's correct.
Okay, so in relation to Soho, what's the distance between Soho and Discovery? Are they within the same range?
Well, so the further away you get, what looks from the Earth as a small distance is actually a very large part of space. I don't know the Soho orbit to know where exactly it is, but there are several spacecraft in the L1 vicinity, but the distances between them are much greater than the distances between spacecraft that are in any particular orbit around the Earth, say.
Okay, so Discover is 1 million miles from the surface of the Earth, or is it 1 million miles from the sun?
million miles from the surface of the Earth, and the sun is about 93 million miles from Earth. So that makes about 92 million miles from sun.
Okay, so 92. So is Discovr equipped to record the active temperatures from the sun?
There isn't a thermometer per se. It measures the energy of the plasma by means of the energy of the protons and the electrons. The protons are measured by the Faraday cup, and the electrons are measured by the electrostatic analyzer. And from that data, one can deduce the temperature of the plasma being a state of energy or a state of matter that is different from a gas or a solid or a liquid, but plasma is disassociated protons and electrons that are thrown out of the sun by the solar storms.
Okay.
So that's the heat energy that we measure is the heat of the plasma itself.
Okay.
And of course the energy of the light from the sun is what you think of as heat. There's some heat in the infrared, some infrared energy, but there's energy all across the spectrum up to the ultraviolet that we sense on the Earth. Hey, it's a really interesting discussion, but I've got other things that I need to handle.
Okay.
And, probably the best thing for you to do when researching these sorts of general questions, there's actually quite a lot that's available on the internet.
Yeah, I've got the information pulled out. I had some specific questions. Are any of is Michael Simpson available? You think he can answer some other questions, or maybe Pat Mulligan?
Michael Simpson's our program manager. I don't know that whether he's available or not. But
what about Pat Mulligan?
He's traveling right now.
Okay.
But
okay. All right. I appreciate it, Mr. Ullman. Thank you for your time.
Okay, thanks for the call.
Have a nice day.
Bye-bye.
Bye-bye. Okie dokie. So, who else could we possibly call? Let me think here, guys. Hold on for a second, because there's somebody else. If I got the Soho information. So I want to call the Soho team. So let me see what we got here. I want to call the Soho team. Okay. So this is what we got here for the Soho team. Science planners. 301-286-4098. Let's call Mr. Bernhard Fleck. Let's call him on Soho. Let's see what he can tell us. They ain't got no damn temperature sensor. They're measuring protons and electrons and plasma. Man, God, why you don't put a temperature sensor on this thing, man? I think I know why they're a million miles away. Because that's a safe zone. Any closer, everything's melting.
Sorry.
Bernhard Fleck
Is not available.
Okay, Bernhard is not available. So let's try to call somebody else here. Hang on. Stand by. Bernhard Fleck. He sounds German. 286-4713. See what's going on here.
Hello?
Amy Fornash?
What?
Is this Amy Fornash?
Yeah?
Amy, how are you? Robert Bassano.
I'm fine, thank you. How are you?
How you doing? I'm a graduate student. I'm working on a master's in systems engineering and simultaneously applied physics at Columbia. So I'm working on a research paper, and it took me into the heliophyseric spheric science. And I just spoke with the guys from NOAA regarding Discovery. So he didn't have much data on the Soho Observatory. So he told me it'd be best that I actually contact you guys to ask you some questions. Is Soho closer to the sun than Discovery, or is Soho further away?
I have no idea. I'm not a space scientist.
So what do you do for the program?
I'm a computer nerd. I don't deal with science.
Okay, you're now. What do you do with regard to far as some computers for the program?
I'd rather not say.
You'd rather not say. Is it?
Yeah.
Well, being somebody who's actually into computers and graphic processing development, is it along the lines of GPU development and image processing?
Nope.
It's not.
Nope.
Okay.
But as far as someone who can actually help you with your questions about science,
who would be the person?
Gurman.
Who?
Joseph Gurman would be.
Okay.
The NASA official in charge of our area, and he should be able to answer your questions or point you at the right person.
Okay, I'll give him a call. I appreciate it, Amy.
You're welcome.
Thank you.
Bye.
Bye-bye. She's doing fucking. I guarantee you that girl is doing image processing. She is probably doing the programming for all of the fake images that they're putting out. I guarantee it. When she says she couldn't talk about it, that is not the first time I've actually heard that. I have actually heard computer people at NASA and these programs say that they can't discuss what it is they're doing. She says she's a computer nerd. So let's talk to Joseph Gurman.
Good afternoon, Joe Gurman.
Joseph Gurman, Robert Bassano.
Hello.
How you doing, sir?
Okay, thanks, and yourself?
Oh, fantastic, fantastic. I just got off the phone with Amy Fornash. She said that you're the best person to speak to about Soho. I spoke to Richard Ullman with the Discovr program and got some data from him with regard to Discovr. I'm a graduate student working on a dual master's in systems engineering and applied physics. So I'm working on a research paper involving developing an API, an artificial intelligence API for advanced image processing. Okay. And it took me in the area of heliospheric science. Now, I've been doing the comparative analysis with Soho and Discovery, and Richard Ullman, he's in charge of the program there. He couldn't tell me much about Soho. So I just wanted to know if you could supply maybe some general open source data regarding where Soho actually is in relation to Discovr, and some of the technical comparative specs. Like, for instance, Richard says that Discovr doesn't have a temperature sensor to detect the actual heat, and he was specific to say that it had to do with the light, but you're measuring the protons and electrons and the plasma coming off of the sun, the coronal mass ejections. Does Soho actually have a temperature sensor?
You're talking about then the solar wind temperature?
No, I'm actually talking about the actual temperature that's being emitted from the sun.
Well, you have to be careful when you say emitted. What the sun emits is three different things.
Okay.
Electromagnetic radiation, light, which includes infrared, but that's a small fraction of the solar spectrum.
Okay.
Or else we wouldn't see things in the visible light.
No. Hold on.
Fields.
Hold on. When you say we couldn't see things in the visible light, now, let me just ask this general question: Is the sun in free space?
The sun is in space, yes.
No, and when I mean free space, meaning, is it in an environment where it's able to interact with other particles, particulates, other matter to allow for light to be visible to us here on Earth?
We get light from the sun. That's why we have day and night.
Okay, because I had read a paper today on the solar physics, the Journal of Solar Physics, and it was pretty interesting. It was a paper to actually discuss ice storms. Ice storms out near the sun. How is that possible?
Well, I haven't seen the paper, so I can't tell you, but near the sun, it's hot enough that you're not going to have water ice.
Okay.
The exceptions to that are on planets that have orbits and rotational periods that are phase locked, so one face to the planet always faces away from the sun. I believe that's the case of Mercury. So Mercury has one face that's actually quite cold because it looks out at the black body temperature of space as opposed to the black body temperature of the sun.
And I love that you brought up black body, because that's actually where my research is taking me, in black body radiation.
Okay, well,
go ahead.
It turns out that most solar physics, including Soho, studies radiation from the sun that isn't black body radiation. We try to, we get most of the information that we get not from the continuous black body emission, but from spectral lines that either are in absorption, that's usually in the visible or to some extent the infrared parts of the solar spectrum, or in emission, which is usually in the ultraviolet and soft X-ray part of the solar spectrum.
Okay.
As well as higher energy stuff like gamma rays and hard X-rays, which usually happens only with intense solar activity. And so there are a variety of detectors on Soho, and some of them look at the solar surface or just above the visible solar surface that we can see from the ground through the atmosphere. Some of them see the more extended so-called corona, which is a very tenuous, low-density medium that's the outermost part of the solar atmosphere, where most of the material is ionized. And we also have things, in so-called in situ experiments. Rather than doing remote sensing, they actually sense, just like the Faraday cup and the magnetometer on Discovr. Okay. They actually sense the solar wind, constituent particles, primarily in our case protons, as well as heavier ions, and so-called solar energetic particles, which happen very occasionally with intense solar activity.
Okay, so
I'm not sure which of all of those you're most interested in.
Well, what I'm particularly interested in is does Soho have a temperature sensor?
Well, when you say a temperature sensor, what do you think of when you think of a temperature sensor? I mean, the ideal case is you have a thermometer or a thermocouple that you stick into something, right?
No, I'm not referring to that at all. See, NASA puts out the data saying that the average or median surface temperature of the sun is 58,000 plus Kelvin.
I think you're off by a factor of 10. It's more like 5,800.
58. Okay, I'm sorry. 5,800. But they don't provide any information to say how they actually obtain that data.
Right. That actually is gotten by the black body curve from visual and other observations from the ground.
So what to your knowledge, what do you believe the actual surface temperature of the sun could be?
The answer is that it's complicated. The sun, if you've ever looked at the pictures and say in the extreme ultraviolet that we take from Soho and other NASA spacecraft and other spacecraft, the structure, the surface of the sun and the upper layers of the solar atmosphere are extremely structured because of magnetic field. Around just above the visual surface, there's a rough equality of gas pressure and the pressure on charged particles like electrons trying to travel across magnetic field lines. As you get just a little bit higher, the gas pressure falls off so rapidly with height that the magnetic field controls almost all the motions that you see, except for in the most dynamic phenomena. So there are some parts of the sun, most parts of the sun will have a black body temperature of something like 5,800 Kelvin. There are some places like sunspot umbra, the dark parts in the middle of sunspots, that are considerably cooler, perhaps 3,500 Kelvin. And there are also some very fine structure elements that are harder to see in most normal photographs of the sun in visible light that can also have relatively low temperatures. And then to complicate that, one of the things that you wouldn't expect, because you know about the second law of thermodynamics, and you expect heat shouldn't be able to go from a colder object to a hotter, is that while the interior of the sun is 10 million Celsius or whatever the number is, and it gets progressively cooler as you go towards the surface. Once you hit the visible surface, the temperature of most of the features in the solar atmosphere go up as a function of distance from the surface. There are some that don't. It's highly structured in the so-called chromosphere and the lower corona. So there are some features that are filled with hot material bound by magnetic field, and there are some that are much cooler. Did I just complicate the problem ridiculously?
No, you didn't at all, because let me tell you what I find to be interesting. The charts that are put out with regard to the exosphere, the temperatures being in excess of 2,000 degrees Celsius or Fahrenheit, whichever number you want to go to. What you're saying to me is that the hypothesized internal temperature of the sun is millions of degrees.
Right.
And then you're saying as it goes to the surface, it cools off, which means, and there's all this plasma being put out into space at whatever distance. So the exosphere, the rest of the exosphere should be extremely hot. Always. Is that correct?
You mean the Earth's axis? You mean the Earth?
No, I'm talking about out in space, beyond beyond the Kármán line.
But we don't talk about the exosphere when we refer to the sun or the heliosphere. There's just the extended solar corona and then the so-called heliosphere. And I don't know what happens in the far reaches.
That's new to me. I've never heard the heliosphere. So you're saying that there's a level beyond the exosphere called the heliosphere?
No, the term exosphere just is not used in solar and heliospheric physics. That refers, as in my experience, to the outermost parts of the Earth's atmosphere.
So the exosphere is what you're saying has been retermed as the heliosphere.
And I'm not saying it's been retermed. I'm saying exosphere refers to the Earth's atmosphere, the outermost parts of the Earth's atmosphere.
Okay.
But if you consider the volume of space around the sun into which the solar wind propagates, that's called the heliosphere. And I don't know if you've heard over the last several years about measurements being made by the Voyager spacecraft as they get farther and farther away from the sun, indicating that they might be reaching the edge of the so-called heliosphere or the solar system or whatever.
Whoa.
And that has to do with the point where you reach a balance in the ever decreasing outward density of the heliosphere and the density of the interstellar medium in which the solar system travels.
Do we have anything that's closer than Discovery?
Closer to the sun than Discover?
Yes.
Not that's operating right now. There was a spacecraft called Helios, actually two of them. They were German spacecraft launched during the late 1970s, if I recall correctly. Maybe one of them was early 80s. But in the next couple of years, we'll be launching two different spacecraft, one NASA and one European Space Agency, to get much closer to the sun, to get to about 38%, I think, of the way from the sun to the Earth.
Wow.
One of the NASA one is called Solar Probe Plus.
Okay.
And the
Solar
European
Probe.
one is and the European one is called Solar Orbiter. And both of them will eventually get out of the ecliptic plane to a significantly, to a sufficient angular separation that they'll be able to see the polar regions of the sun better than we can from here in the ecliptic.
But let me ask you a question, because I've seen a computer model which was pretty interesting. It was an interesting computer model, and it showed all of the planets spiraling around the sun, and the sun moving in a linear fashion heading, you know, what I learned in
its orbit, and go on.
Yeah, what I learned when I saw this model supported what I was learning in the classroom, that the universe is speeding away from us in the opposite direction at over 90 million miles a second, which means that we're going in the opposite direction.
The universe is expanding.
Okay,
so space itself is expanding. So any place you are in the universe, everything seems to be expanding away from you.
Okay, now when you say away from us,
then there's the fact that the solar system is in a spiral arm of the Milky Way galaxy and is revolving around the center of the galaxy.
So where are we going? Where could where when I saw this model, where could are you saying that we're not moving in a linear fashion, but we're moving around in some sort of elliptical type of spiral?
I don't know if it's elliptical, but we are in a spiral arm of a galaxy that's roughly, you've seen pictures of galaxies, right?
Yes, sir.
That are end on, and they have these spiral arms. The Milky Way, we believe, is like that. We're in one of those spiral arms. You can tell that because of the density of stars around where we are. And we know that that's rotating around the center of the galaxy at a certain rate. So that gives us a rough idea, especially when you measure the shifts from rest wavelength of spectral lines very accurately from reference stars at different places in the sky. We know roughly the direction that the sun is headed. I think it's somewhere in the direction of the constellation Lyra or Hercules or someplace like that.
Okay.
And roughly what the speed is. So if you were to, say, okay, over some relatively short part, like 10 or 20,000 years worth of the sun's motion, it's far enough away from the galactic center that you can approximate it by a straight line. It's not that different. And if you were then to plot the motions of the planets around the sun, that would look like a spiral. Because it'd be orbiting around the sun in the plane of the ecliptic, but that whole plane would be translating around the center of the galaxy.
What was the distance? Refresh my memory. What was the distance of Mercury from the sun?
You can Google it. I don't know it off the top of my head. I think it's about 0.3 of an astronomical unit, where astronomical unit is the mean distance between the Earth and the sun. Okay, so let me say something probably that's going to be foolish. Has anyone ever thought about literally deploying a solar monitoring asset that literally could shadow the Mercury and follow it around as it goes around the sun, and it could be shielded from all of the heat and the radiation? You're a good engineer. You just identified the biggest problem, which is shielding, which is why the Solar Orbiter and Solar Probe Plus won't get quite as close to the sun, I believe, as Mercury, or at least not much closer. And it's because of the difficulty of shielding instruments and spacecraft subsystems. Both of those spacecrafts have very serious heat shields on their sunward-facing sides. And then you're dealing with another problem, which is that typically, if you're in the inner solar system, you get the electrical energy for your spacecraft subsystems and instruments from solar panels. If the same solar panels that work just great at one astronomical unit, where we are, if you bring those into where Mercury is, they just kind of ablate, they melt, or they produce so much power that they destroy something.
So it actually has to do with the problems we're having. Well, actually, the problem you guys are having is that we don't have the technological capability to develop some sort of nanomaterial where literally the black body radiation can be converted into some sort of capability to harden the actual metal or the substance that would make up the composition of the actual satellite.
It's doubly complicated, actually triply if you include the solar array. Because
that's where my research paper is headed. Is that I believe that there's a way
that can survive, and I'm just looking at this up on a site called 9planets.org. Mercury is 0.38 the distance of the Earth from the sun. It doesn't have a terribly circular orbit, but that's the mean distance. And at that distance, you can't use the same materials you would use for shielding at 1 AU. And kind of anything that you leave out there exposed you're gonna have to engineer to survive that kind of thermal load. Now there are systems that will allow you to radiate it away on the backside of the spacecraft if you keep one side facing the sun all the time.
Okay.
But that also means that if you have instruments that would like to have large collecting areas, like let's say telescopes, they can't be facing directly, to the sun, because then you'd have this big hole in the heat shield and the interior of the spacecraft would get too hot.
So of course heat is the issue.
Sorry, go on.
Yeah, so heat's the main problem. So the distance that these assets
there is to use very small aperture telescopes, because after all, if you're 2.5 times or whatever it is closer to the sun than the Earth, then you have 6.25 times as much radiation. You can get by with a smaller telescope. And the idea is to look through so-called soda straws that have a very narrow angular aperture, and the insides of which are made of the same material as the thermal shielding, to reject heat that doesn't come directly down the telescope tube.
Okay.
And then you also have problems with things that hang off the back of the spacecraft, because that's where you have your maneuvering system and communications antennas and so on and so forth.
Have you guys ever thought about this? We've been using balloons for God knows how long, and I know that there's been several balloons developed specifically to use solar radiation and light and heat to keep the balloons aloft. So take this under consideration. Why not deploy one of these solar monitoring satellites, which would be equipped with, say, several balloons, and then at different stages, the balloons will deploy. Of course, they're going to immediately expand.
What keeps a balloon aloft?
Heat, expansion, lower density.
The balance of the forces of gravity and the difference between the density of what's inside the balloon and the density of what's outside, right?
Yeah, exactly. But is Soho at the Lagrange range, at the Lagrange distance, where everything is like, there's this area where everything is like almost stationary?
Well, it's not stationary, but the best way to describe it, I don't know if you've ever come across anything that can be mathematically described in terms of saddle points, either kind of peaks in a potential or wells. Okay. But it's at an unstable saddle point, which means if you push it off in any direction, it tends to go away from that point. Okay. But as long as you're in that vicinity, you get pulled by the sun. If you're moving in a straight line, the forces pulling you back from the sun and the Earth are roughly balanced. Okay. So you end up in an orbit, if you can get a closed orbit, which is difficult. You end up in an orbit that orbits the sun in lockstep with the Earth. Okay. There are also more stable points in the solar system, or actually in the Earth-Sun system, like L5, L4, and L5, which are better for putting spacecraft at, because you don't have to use as much maneuvering fuel to constantly trim the orbit, or continually, I should say, trim the orbit, as Soho we do it every 3 months, just to keep the spacecraft from getting too far away from the Lagrange area. Okay. So when you say getting too far away from Lagrange, you're talking about getting closer to the sun based on its magnetic pull? The orbit in which it was placed is mostly in a plane perpendicular to the Earth-Sun line, so that it doesn't get a whole lot closer to the sun. But if it were to break away from the Lagrange area at some point thousands of years later, it might end up diving into the sun. It might end up being captured back in the Earth-Moon system. It's kind of a crap shot. There's just little perturbations can affect the orbit. Well, why doesn't that happen to us? To us, because the Earth is a large massive body that's just rotating around the sun, in an orbit around the sun. If you put something in a Lagrange point between something the size of the Earth and something the size of the sun, you end up with one of these Lagrange points, among others, that's about 1% of the way between the Earth and the Sun, because the size of the Earth is about 1%, in diameter of the size of the Sun, and things go as 1/r squared.
Yeah. So
is the solution that falls out.
When we do the comparison to the size of the Earth and the size of Mercury, Mercury being well within the Lagrange point, closer to the Sun.
Well, that's the Earth Lagrange point. There would also be a Lagrange point for Mercury. It's probably, once again, 1% of the distance between the two of them. Doesn't help you. The only spacecraft that I know of recently to have visited Mercury, and I think the first one to go into orbit about it, was Messenger, that was launched, can't remember anymore. Took a long time to get to Mercury because, again, it sailed around the inner solar system until it encountered the planet. But it was in a kind of large eccentric orbit because it was primarily designed to sample Mercury's magnetosphere. And it had a heat shield that was especially useful when it was on the sunward side of Mercury and not being shielded by the planet. But that also meant that it didn't have any solar wind instruments that could sample in the ram direction the spacecraft was flying if that was towards the sun, nor did it have any optical or UV telescopes.
I'm really loving this conversation because you know what you just did. You just now got me questioning the level of electromagnetism that the sun may not have, because what you just described with Mercury and it being smaller than the Earth and closer to the sun just can't have that much magnetic strength to draw in Mercury. Or Mercury,
It's not magnetic strength, it's gravity that holds it bound, just like it holds the Earth. In fact, the sun has intense magnetic fields. The magnetic fields in sunspots are of the order of 2,000 or 3,000 Gauss.
But with Mercury being the size it is, it just for me I'm starting to question the logic behind. Yeah, okay, they both have gravitational fields, but the sun's gravitational field is supposed to be 100,000 times greater than Mercury, but somehow Mercury is able to keep its distance for this, for its entire life.
We have Isaac Newton to thank for the understanding of that.
Newton.
Yep. It's really simple. He drew a very simple diagram in his book called Principia Mathematica.
Wait, what was the name of it again?
Principia Mathematica, the principles of mathematics.
Oh, okay.
Imagine that you got a really high mountain so you can actually kind of see it on the edge of the Earth or any other planet. And you had a gun with a certain muzzle velocity that fired a projectile. If the muzzle velocity wasn't particularly great, it'd start off traveling in a straight line. The projectile would start off traveling in a straight line tangent to, let's say, the diameter, to the circumference of the Earth. But it would be drawn in by the Earth's gravity. So it would describe part of a parabola as it fell back to Earth. Then imagine that you fire the projectile with a greater velocity. It gets drawn back to the Earth too, but it gets farther than the first one did, just because it takes the same amount of time for gravity to pull it in, but in that time, it's traveled farther in its quote-unquote straight line that it would have traveled if the Earth hadn't been there. Depending if you want to look at it in Newtonian mechanics, gravity pulls it in, or in the terms of general relativity, because the mass of the Earth warps space-time, and so the natural direction for it to travel is along a so-called geodesic. But then imagine that there's some critical velocity that you can fire that projectile with, and it never falls to Earth because it falls all the way around. That's a closed orbit.
Okay.
So when you say you achieved orbital velocity for a manned spacecraft or an unmanned satellite or whatever, all that means is you've gotten that projectile going just fast enough in that quote-unquote straight line that it falls around the planet, all the way around the planet, and keeps going around and around.
But eventually it's got to slow down.
No. And if it were really empty space, it wouldn't slow down because there would be no friction. It would just keep going. You gave it enough energy to get into a bound orbit. Now, if you're in low Earth orbit, in the exosphere of the Earth, there are enough molecules or atoms or ions that you eventually have collisions with them and they slow you down. But it usually takes a while. And that's more likely the lower the orbit is. If you get it out to 22,000 miles, which happens to be your time to make one orbit is locked to the period of 1 day, so you can remain above the same longitude on the Earth the whole time. And if you're over the equator, you remain over the same point all the time. Then there's almost no friction, and you can stay up there almost indefinitely.
Yeah. Yeah, you know, I was working on a paper and I found a quote by James Beatty, and he says, "We live in a Newtonian world of Einsteinian physics ruled by Frankenstein logic." And I'll be honest with you, you know, since I studied and I took my first introductory course in physics, you know, the first question I asked the first week of the professor was, we started discussing Newtonian laws and discussing gravity. And I asked the proverbial question, "Professor, what's really happening at 9.8 meters a second?" And he just paused for a second. He says, "Let me show you the math." I said, "No, I understand the math. What's happening? Why can't we duplicate it?" He goes, "Yes, we can. Hold something up and drop it." I said, "Well, wait a minute. If I compare that to what Tesla was claiming, where's the problem?" I said, "You know, we're reading the textbook, 542 pages, and there's one sentence in a summary section in the physics book talking about Tesla. So could pressure have anything to do with it?" He says, "You know what?
No, it works just the same if there's no electric field on the planet."
Well, what's interesting is that we're still looking at Newton's laws of gravity as a theory. And
well, you got to watch out there. The way theory is used in science is different from the way it's used by most people in ordinary everyday speech. Okay. Theory just means here's a hypothesis, and usually by the time it gets to the status of a theory, it's a hypothesis that's supported by all the observations we've ever made, the measurements.
Would you agree that those observations are just a collective concurrence and agreement of this is what it is and it can't be anything else?
That's another problem with,
based on perception,
different concepts of what the word theory means. In physics, theory usually means that it's both necessary and sufficient, and that there are no good alternative explanations.
Oh, and
So right now, for instance, although we've had literally 100 years, it's been 100 years since Einstein published his paper on the general theory of relativity. We've had 100 years with people coming up with alternatives to the general theory of relativity. Some of them are different forms of relativity. Some of them are all kinds of different stuff.
Yeah.
But so far, every observational test of general relativity has proven out, whether it's the equivalence of masses undergoing acceleration or the difference in the speed at which clocks run if they're in different frames of reference. Say you put a clock on an orbiting spacecraft and run it for a few years, and you know what speeds it's gone through and what distance it's gone through, and you compare it to one on the Earth where the surface is rotating at a certain rate, and you notice differences between the two. As a TV show a couple of weeks ago on PBS pointed out, you can even measure, if you have a really good atomic clock, you can even measure the difference in 24 hours in a clock at the base of a mountain and on the top of a mountain.
Yeah.
So there are so many observational proofs of general relativity, including the recent first and now second measurements of gravitational waves. We're pretty sure that it's the theory that works. It doesn't mean there might not be further elaborations, but to the level of accuracy that we've been able to measure any of the multiple phenomena that it predicts, we're pretty sure that it's right.
Have you ever heard of Eric Dollard before?
No.
He says that he studied the sun for 4 years at Sonoma State, and during that time they were studying sunspots, and one sunspot in particular they were studying got large enough to where they decided to see if they could peer inside of it. And hold on to your horses for this one. He says peering inside that sunspot he realized something. There was nothing inside.
That's not true.
Well, I'm not. I didn't say that. Yeah, I'm not saying that it's true. I'm just saying that that was a statement that he made, that the sun's not burning anything.
It's just wrong. If you want to see the best image of a sunspot that's been made from the ground, you can Google highest resolution image of a sunspot, and there are a whole bunch of pictures you can see there. And the best one is one that was just published a couple of years ago. Actually, I think there was one published more recently, but from Big Bear Solar Observatory in California.
Okay.
There's this, you just Google space.com and high definition images of the sun. You can see some of the structure in the dark so-called umbra of a sunspot. You have to have really good what's called stray light suppression in a telescope in order to see this stuff, which means that, you know, here's the solar surface, the so-called photosphere. It's 10 times brighter than the inside of a sunspot. There's going to be scattered light on the inside of a telescope that's going to distort the image, the light that you see from the umbra, unless you suppress that off-axis light and the light that could be bouncing around inside your telescope. And you get this whole system of cells and dots and you know, all kinds of stuff.
Yeah, it was interesting that he said that it's definitely something to consider. And based on what you told me with regard to how the sun actually...
Trust me, Sonoma State doesn't have the instrumentation to make that statement.
Yeah, I'm pretty sure of that. I'm pretty sure of that.
Yeah.
Pretty sure of that.
Now, when the instrumentation was even worse, about 100, whenever it was, 70 or 80 years ago, Herschel, who was one of the great astronomers of the early 19th century, believed that, well, it was cool enough in sunspots that, you know, it was probably an atmospheric phenomenon on the sun, and there could be people living there, you know. Well, sorry. It doesn't
people
work that
living
way.
on the sun.
Yeah.
People living on the... That sounds like an interview I heard with that guy, talked to Buzz Aldrin. He says, can we land on the sun? And he just looked at him and he says, are you crazy? You can't, the sun is too hot. You can't walk on the sun.
We'll go at night. Yeah, I know. Right?
Yeah, we'll go at night. What's your idea on what the rest of space could be with this research they're doing on superfluid helium and dark matter and dark fluid?
Dark energy and everything else, I have no idea. That's so far out of my area of expertise that I just wait for the articles in the popular press like everybody else. Doesn't mean I couldn't go a few buildings, you know, half a mile across the campus here and ask some astronomers, but that's just not my field of expertise.
Okie dokie. You were a tremendous help. It was tremendous help. I really appreciate it. I've got a lot to remember and review and go over. I've jot down all the websites that you had mentioned, the information, and I'd love to have another future conversation with you. I want to put everything together succinctly so that I've got a direction with this to discuss this with you, because Discovr, they're doing their thing. They're kind of busy. Soho, you know, everything that's out online that everyone's reviewing is from Soho. So, you know, I guess this is where I'm going to be getting most of my information from. I'd love to see what those new assets are going to be doing and how close they're going to be getting. That whole idea of using Mercury is sort of a protective, how should I say, natural shield to literally develop something to get close enough where it can literally stay in geosync orbit with Mercury as it goes around the sun and kind of play like a hide and seek, kind of peek out over the horizon of Mercury to peek at the sun, you know, at certain times and then come back down, you know, to hide behind it.
It turns out that you don't need to get that close to do the kind of measurements. You can just put a bigger piece of glass in like orbit around the Earth or at L1.
So what's James Webb going to be doing? Is James Webb going to be pointed at the sun as well?
No. That would destroy destroy that. That's an infrared telescope, and in fact, its orbit is it's going to be in orbit around the L2 Lagrange point on the other side of the Earth from the L1.
Okay.
Beyond the orbit of the Moon, specifically, so that the Earth is able to shield it a great deal of the time, so that it's the backside or the sides of the James Webb Telescope won't be getting direct sunlight at least some of the time, so that its store of cryogen will last longer.
Okay.
Because it's going to have infrared sensors, and those generally are only efficient and low noise if you get them really cold. And you can only get them so cold with mechanical radiators. Generally, you need to use an active cryogen source, like some liquid helium or something.
Yeah. Hey.
And that boils off after a while. You get a finite lifetime.
Have you ever seen any of those images taken from space where the sun is actually projecting the sun rays down onto the Earth, and it gives the appearance that the sun is actually closer?
Yeah, that's just an artist's conception.
It's an artist's conception.
So they can get them both in the same picture,
Oh, so the images that are being put out there online, where they show the sun just having
and the
this,
Earth in the same picture.
Yeah, and the same.
Not going to work.
So those are all.
The sun's radius is the radius, if I recall correctly. Is less than 1/200th of the distance from the sun to the Earth.
So when we look at the live ISS footage, what are we seeing?
Pardon?
When you see the live ISS,
those pictures with both the sun and the Earth in them, either they're taken from a heck of a long way away, like Saturn or Jupiter or someplace, or they're just artists' conceptions.
Whoa! Hold on, Joe. Hold on. Let me make sure I get this right. So if I go to ISS Live right now, the live stream that NASA has, and that they're doing the sunrise and sunset, you're saying that's.
Oh, okay. I see what you mean.
Okay,
we can see that on Earth too, right? You can see the sunrise.
Yeah, the sunrise. But when they're
talking about seeing the entire Earth and seeing the sun in the picture, you have to be farther away.
Okay. But from the ISS, when they show and they're doing an EVA and they're showing the sun, I mean, literally, no camera should be able to see that.
I mean, the ISS is only a couple hundred, nautical miles above the Earth.
Okay.
So it's not very different from being on the surface of the Earth in terms of what does the sun look like in the sky. It's just that the sky you see the sun in is black when you're on the ISS. Okay,
because I asked the ISS team, I asked them, did they have any temperature sensors out on the ISS to record the external temperatures when they do an EVA, and she said that it was minus 200 degrees Fahrenheit, plus 200 degrees Fahrenheit. But
depending on whether or not you're in the sun. And so that's one of the interesting challenges in engineering a spacesuit. If you're out there during the time when the sun is shining on you, the sunward side of your suit is plus 275, and the back side of the dark side of your spacesuit is minus 275. That's a pretty challenging engineering.
Yeah, that's really challenging. And based on what you told me, what the temperatures are, if the temperature is at 5,800 degrees Kelvin, once that light is reaching the astronauts on the ISS, it should be great. The temperature should be greater than 275 degrees.
No, that's the right number.
Really?
Yeah.
So they can't be out in free space. They're still in our atmosphere.
No, they're out there in space. It's just what happens when the radiation gets diffused through, as we would say in mathematics, 4 pi steradians at a distance of 1 astronomical unit, which is, as I said, is more than 200 solar radii. So you're taking the same amount of thermal energy that's coming off the sun, and you're distributing it over a much vaster surface area. Imagine a sphere containing the sun in the middle that had a radius the size of the Earth's orbit, 1 astronomical unit.
Interesting.
Then the amount of heat that gets, if you will, radiated onto any 1 square centimeter of that bigger imaginary sphere is much less than what comes out of 1 square centimeter of the sun's surface, because that's expanding to fill that whole space.
Okay. So I know that you got to work. I'm going to ask you one last thing, and it's more of a mathematical logic for me. The math says that the Earth is rotating around 900 nautical miles, maybe 1,100 nautical miles, right? An hour.
You mean the rotational
the
speed
rotation
of the Earth?
the
That
rotation
depends
of
on latitude.
yeah, so it's about
That'd
1,000
be
miles.
the equator, maybe.
Yeah, so about 1,000 miles an hour, right? Okay.
That sounds reasonable for the equator. Yeah.
All right. So, and we're supposed to be moving around the sun at what speed? Like what, 67,000, right?
I honestly don't remember the number, but
Yeah,
figure it out.
somewhere around there. And how fast is the sun rotating?
The sun, once again, it changes with latitude, and not quite like the Earth because it's not a solid body.
Okay.
But at the equator, it's about once every 28 days.
So, in relative speed, what are we talking about?
Relative to
the Earth.
Well, it takes us a year to get around the sun.
So it takes us a year, but
12 or 13 times as fast.
12 to 13 times as fast. So when we put all that mathematics,
revolve around the sun.
Yeah. So when we put all that math together,
I'm not sure how.
That's what I'm saying. I'm real dizzy just even thinking about it right now.
The rotation speed of the surface of the sun doesn't amount to much, except in terms of carrying things like active regions, which are magnetic active regions, by the line connecting the Earth and the sun. So you'll see variations in the solar wind speed, in the density of the solar wind, in the proton temperature, and in the magnetic field strength and direction as various solar wind features that are connected to the surface of the sun rotate past you.
Wow.
That's about where you see that. And that was first noticed in I think the second half, or maybe in the middle of the 19th century, when people started building what they called magnetometers on Earth, which was basically an accurate compass needle, if you will, and looking at the deflections of the compass needle from the nominal direction of the Earth's magnetic field as the variable magnetic field from the sun went past us at that rotation rate.
Okay. Wow.
But it's clear that the rotation rate of the Earth, no matter how large it seems as an absolute number compared to driving your car down the street, is small compared to the effects that we all feel, just getting up out of a chair or sitting down. We don't notice which way the Earth's rotation is if we're just walking.
Yeah, and that was another issue too, because I've been running across research where everyone's using this standard FEM model, flat Earth model. They're saying that the fixed plane, the plane surface of the Earth is fixed, and the rest of the outer layers of the atmosphere are actually rotating at these speeds. So everyone's using it. I mean, I've been finding it in every single physics journal I've ever read. Freeman Dyson discusses it. NASA discusses it. They talk about the non-rotating stationary Earth plane. I mean,
they want a reference. There is no fixed point in space, so you have to have some reference relative to do things. So, like when you see a weather map and you see weather patterns, flowing over, let's say, the continental United States or in North America. Yeah, of course, North America is rotating around along with the rest of the Earth, but you don't care about that because you live where you live in North America, and you're interested in what weather front is coming through here. Is it going to be hotter or colder tomorrow? Is it going to rain tonight? Yeah, stuff like that.
So the model that they're using, because there's no spherical mathematics for a rotating sphere, the fixed reference, they're saying, okay, I
can assure you that in climate modeling, they do use a spherical model and
they use
geometry because they have to include Coriolis force and stuff like that.
Coriolis.
Exactly what you were talking about, the fact that the Earth is rotating in the atmosphere with it. And in fact, we use it. Coriolis is an important effect in the sun too, and we're trying to understand convection in the interior of the sun.
When I read Einstein's papers, they were trying to actually develop some science and device to measure the rotation of the Earth by putting an object on the ground, and they were never able to do it. They said it couldn't be done. They said that it was the ether that was moving, not the Earth itself.
That was what was believed before the Michelson-Morley experiment.
Yeah, Michael. Yeah, okay. Yeah, it's getting really complex. Really complex. You've given me a lot to think about, Joe. I really appreciate it.
The engineering is really complex for science.
Yeah, that's why I'm going systems engineering. I'll leave all of the complexity to everyone else. Just tell me what you want me to design. Just tell me.
You'll find plenty of complexity in it.
Yeah. Well, just tell me what you want me to design and let me figure it out, and then whatever you're going to do with it, that's your business. You know, if you want to
have to help me define the level 1 requirements. I can't do it on my own.
Yeah. It's just one. I mean, after all these years, we're still trying to figure out the construct, shape, and design of the Earth. We're still sending up sounding rockets. We still can't determine, you know, how far we can go. You know, how are we going to get there? I mean, you got Don Pettit talking about the tyranny of the rocket equation, confusing the hell out of everyone, saying, you know, we got to eliminate all dumb mass. But wait a minute, didn't you just launch something that's 50,000 pounds? What are you talking about? You know?
Yeah, but it's incredibly expensive.
Yeah, it's incredibly.
If you're really talking about, you know, setting up colonies on other planets, we just can't keep doing it the way we've been doing it. Something has to change.
Yeah. Okie dokie. Joe,
anyhow, good talking to you.
It was good talking to you too. Thank you very much. I really appreciate it.
Yeah, you're welcome.
Have a nice day. You too. Take care.
You too. Bye.
Okie dokie, people. That was an interesting conversation. Let me stop the share screen and let me invite some people on up in here. Okay. Get some people up in here. If you want to come in, and talk, let's talk. Please. If you want to come in, please come in. Let's have a chat. Anybody come in. If you act stupid, you're going to get banned. That's all I got to tell you. Don't act stupid, please. Flat Earth Horizons, I'm going to give you a hammer. I like you. Who else I want to talk to? Rockin', my man. Come on in. I put the, remember be cussing all out if you had to do it 24 hours a day. Nah, I can't be cussing with people, man. Listen, please, man, if you're out there, please come in here. Let's talk. Let's talk about this, man. Please, let's talk. Please, let's talk. Who is ever out there? You there, Event? Ronnie.
Yeah, man. Great job. Great job.
Oh, dude. That was crazy, man. That was crazy, dude. I learned a lot on that call.
Yeah. Once you got past the traveling guy, the second call, you know, this one was good.
Dude, that was a good ass call, man.
Yeah, I never knew the sun rotated 13.3 times every year.
I didn't know that either, man.
Yeah.
I didn't know that, dude. That was crazy, man. I really enjoyed that conversation.
And then he admitted to plain.
I enjoyed that. I'm learning, dude. I'm a student, man. I ain't no I'm not a physicist. I know something about systems engineering, but I'm no physicist. I'm learning physics, man, and I'm learning it because I want to understand. But you see how I just slowly had to slip in that flat earth stuff, bro? I had to slowly slip in. You can't just come out and say that, man. You just can't come out and be aggressive like that. You just can't do it.
Well, he didn't deny it, you know, and he brought up the Michelson-Morley experiment too, which was...
Yeah, he brought that up too. Yeah, he did.
I don't know if he's alluding to the failure, but he left that word out.
Yeah, this just proves to me I got to do a lot more research, dude. I got to do a lot more. And it's good, man, because it gets me thinking, you know what I mean?
Yeah.
What is on my screen right now? Oh, you're doing the share screen.
This is the Big Bear that he told you to go look at.
Oh, yeah.
It's an Earth observatory or whatever.
The Earth observatory, yeah.
Further here, he said, if you want to see the best images, go here. He didn't send you to a satellite. He sent you here.
That dude who did the Discovr information from NOAA, he didn't know nothing.
Mm.
He didn't know anything about that damn thing, which was strange to me. You know what I mean? This guy, he broke it down.
Yeah.
He broke it down, dude. I want other people to come in, man. Just please, let's talk about this, man. Anybody want to come in, just come in. Who else is this?
Maybe we should put the
Crazy,
link again. It was.
That was a crazy call, dude. That was. I want to do more. I really do have to do more. I really do have more calls, man. I'm gonna try to do this every Monday, dude.
Yeah, no, I think you're doing a great job, and it seems some of these guys are kind of happy to get off the chair and on the phone, man.
Yeah, they are, dude. Because we're gonna learn a lot, man. And again, a lot of these calls ain't gonna be about proving flat Earth and that. I mean, it's just talking about science. I mean, we want to understand this, man. You know what I mean?
Mm-hmm.
We just can't keep running around, you know. And yeah, I'm putting the documents out, and I want to understand. He says, well, they're using it because they need some sort of fixed reference. You know, that's what he's saying. They're using
he said the
model as a fixed reference.
Artist rendition too.
Oh, dude, when he said that, dude, that was crazy. When he said that. When he said the art that most of the what you see, the images that are out there, when they show the sun and the earth in the same image, he says, "Oh, those are confused artists who put together those photos." I'm like, "Oh, hell no!" Dude. I was like, crazy. And then what he said about when he said about the with the ISS, he was saying, "Yeah, that's what the temperatures are." I don't know, dude. They don't have no temperature sensors. That's the thing. They don't have temperature sensors on these satellites, man. He says they're measuring the plasma and protons and everything coming from the Faraday cup from that one satellite. But why wouldn't you put a temperature sensor out there? That's what gets me, man. It's like if you're collecting these highly charged protons, right? That means that Faraday cup is getting bombarded with that shit. You know what I'm saying?
Yeah.
I mean, you're talking about the sun. You're talking about the sun. That shit's got to be bombarded, dude. Which means that thing could actually break down if it gets too much. He said it himself. He says if one of those satellites gets too far away out of the Lagrange zone, they lose it. It'll melt.
Yeah,
he said it will melt.
What was funny? Hey guys.
Hey, how you doing, man? It's crazy, dude. It was crazy. I mean, I'm gonna be looking into both those satellites. You better believe it. I haven't looked into them extensively. I did that on the fly, bro. But I'm definitely gonna be looking at the technical specifications for both those satellites, bro.
He also admitted that satellites flying above the equator, they fly forever. He was saying, right?
Yeah, which is strange, dude. I heard that.
Yeah.
Yeah, I got to get some more calls together, bro, because I'm not confused now, but it's got me wanting to look into other areas. It definitely has me wanting to look into other areas, bro. For sure.
That was a good call, Rob. That was pretty good, man. You had him, and then when he admitted that everything was printed up by artists and stuff, I was like, oh boy.
Oh yeah. Yeah, that was good. I mean, I didn't have my questions prepared. It was just, hey, let me just shoot from the hip. You know what I mean? And I wish I'd have had some other people in here who actually have been putting videos out about the sun and all that kind of shit.
He sent you a picture with a sun showing an empty sun.
Yeah, that's crazy, dude.
Yeah, I'll put this in the chat, this link. Wow.
It's just crazy. It's just crazy, dude. I got to do some more calls, but I need to put the questions together, man, because I got to research the data. See, the thing, I'm busy, man. I'm collecting a lot of stuff, but I need help researching the shit so I can put together sort of, okay, can you explain this? Can you explain that? I read this. I read that. There's a lot of data out there, dude. Yeah. There's a lot of data out there, man.
I think you did a great job. Just off the if that was off the hip and what you did, I think it was brilliant, man. I mean, he acquiesced. He threw a couple things out there that I'm sure, in hindsight, he's gonna, after he hung up the phone, he's like, oh shit, pardon my French, but he probably did that. I think it was great, even without prepared questions or anything. Off the cuff, yeah. It was great.
I can tell you this right. I'm probably gonna run into some of these people and be like, yeah, you're Robert Bassan, right? Yeah, you put out that video on me, didn't you? Oh, dude, I mean, man, Man, I don't care, man. I'm curious, man. I just gotta know. I have to know.
Well, it's funny. The one lady just went right to, whoa, hey, I'm a computer chick, man, a computer nerd. Don't talk to me. You got to talk to this guy.
And I asked her what she did. She was like, I'm not at liberty to say. I'm like, what? What the hell? What the hell? I'm like, are you doing graphic processing? I think she's actually processing the image, man. She's one of those people he talked about.
Yeah.
That's what I think.
Yeah, very well could be, because that was like, I mean this in the sense I'm saying hot potato. It has nothing to do with another chat. It was like a hot potato, and just pass it and get the hell away from me, and I'll see you later and goodbye. Lose my number.
Yeah, that was crazy, dude. I gotta start doing some real reading and getting deep into this and using it. But just for everybody out there, for the record, man, the flat Earth model mathematics they're using, he said it. It's being used as a fixed frame of reference for everything they're doing in the sky.
Yeah.
So, and I'm not going to say that he was confirming that the Earth is stationary, but what he's saying is that they're using that math and that science because they need some sort of fixed frame of reference for everything else they're doing.
Yeah.
Now,
very true.
I've always said that I believe that the upper atmospheres are rotating. That's proven. Because when we look at the star trails, what do we see? We see those stars moving around in clockwise, counterclockwise. You know, you standing still. I never felt like I've been moving. Never.
No.
But the only way to know you're really moving, man, is get up there on a high altitude balloon and really stay still and see for yourself if you're really moving.
Yeah, absolutely. Hey, Justin, I didn't see you in there.
But that's strange, dude. They all sticking to the story that the sun is 93 million miles away. But see, what then makes sense to me is this, right? Knowing how big the sun is supposed to be. He says that the temperature internally is millions of degrees, right?
Yep.
Millions of degrees, and then all of a sudden, when the surface on the surface of the sun, it's like tens of thousands of degrees. How do you go from 1,000,000 degrees to tens of thousands that fast? You understand what I'm saying?
Yeah. Oh, yeah. Totally. I'm still trying.
It doesn't make any sense to me how literally the heat from the sun could be cooled down that fucking fast, man. It just doesn't make sense to me. It still doesn't make sense. How you can go from literally millions of degrees to 5,800. To 5,800 at about 1,000 kilometers out, or 10,000. Let's just say 100,000 kilometers out.
Right.
The temperature is less than 10,000 degrees. That's what he's saying.
Man, I don't. When he started with it, that's also spinning. I'm like, I think of the old days when you used to see the old carnival show where everybody's spinning plates on their fingers and stuff, and he's like, all right, it's spinning also. I'm like, wait a second, what?
Hey, Rob, actually, that's an equation. If you can figure out the degradation of the temperature versus the distance of the sun to the Earth, you can figure out how hot it should be before the heat reaches the Earth, and probably bust that whole theory.
I think it was pretty cool how he kept talking about the heliosphere. Meaning,
I never heard that before. That was interesting. You're right, Justin. He says they don't use the exosphere anymore. He said they talk about the heliosphere.
Meaning containing the sun.
Yeah. Exactly. Which means that's why I was trying to get him. I was trying to get him to admit that if he's calling it the heliosphere, that means that the sun is closer.
Absolutely, yeah.
Or even in it.
Or what he was saying, the heliosphere means the sun is inside the heliosphere.
Yeah, I mean, that's...
It ain't... I can't... Sorry, dude, I can't... Dude, I got to start over, man. I got to start over. I got to start over with all the things that I said, man, regarding where the sun could be, because I was using the 5,800 degree Kelvin temperature to go from the surface of the Earth to low Earth orbit, which is somewhere around 1,242 miles, right? 1,242 miles. You do that geometry, you would get a rough idea where the sun could be, which is somewhere between 800 to 2,000 kilometers. And then when he told me about those images we saw of the sunlight reflecting down onto the Earth, making it appear that the sun was closer, I gotta do that shit all over again, because I was using those images that we were getting from NASA. That's what and then when I found out about the surface temperature, he debunked me, bro, on that one, because what he's saying is that the internal temperature of the sun is millions of degrees, and then when the heat is put out, it cools off, which means that the temperature they recorded, NASA recorded 5,800 degrees Kelvin, is completely wrong, bro. We got to go with million-degree temperatures. But then their science could all be wrong. They could just be putting that out to lie to us, bro, to make us believe the sun is far away. Again, the only way you're gonna know is go up in a high-altitude balloon and see it for yourself. And see it for yourself. You can't. This goes back to my simulated universe theory, man. My first video. Ain't nothing real. This ain't real, man. This can't be real, people. There's no way. They know we can't get up there, so they just put this science out, and it's all convoluted and mixed up, and you're like, man. I mean, he even says, did I just complicate things for you? Hell yeah, you did. Hell yeah, you complicated it.
Yeah, exactly. Because you're going off of what everyone is taught, and he just changed it around and said, "Am I complicated?" What you already know.
You can't trust the data. You cannot trust the data.
Exactly.
You can't trust that. I'm now. Here's where I'm at. I can't collect any more documents and put them out until I review it and make sense of it myself. That's where I'm at with this right now. That's how I'm feeling about this. I can't even talk about this with nobody anymore until I literally get all that documentation, put it on the floor, read it, highlight this, highlight that, and try to make sense of it and do the math and say, okay, let me see here. Is what this guy just told me, is this correct? Is this possible? And then I make a decision to say, okay, I'm going to run with this because they can't prove this, so I'm going to say this is bunk because they can't prove it.
So break down what you think he meant when he was talking about the artist rendition, or...
Oh yeah, the artist rendition. We already knew that, Justin. We all knew it.
But he was saying that it was either taken from far away, like Jupiter or Saturn or something, or it was an artist rendition.
No, it was an artist rendition. There ain't nobody fucking taking photos. Yeah, nobody taking photos from fucking Jupiter or Saturn, dude.
Yeah, we know that. We know that. But I just meant as far as what he was referring to, like the sun and the earth in the same picture, I think, something like that.
Yeah, he said it ain't possible.
Yeah, he did. Yeah.
That's what he said. He says it's not possible to take a picture of the sun and the earth in the same photo. Now, when I showed you guys, when I did that share screen of where Epic actually was, and you look at the distance, I'm going to pull all those links inside this thing here for the description for people to look at it. What he's saying is that there ain't no way you can capture the entire Earth and the sun in the same photo.
Yeah, he did say that, and that surprised the hell out of me because it's like
that shocked me too.
Yeah,
because
I was like, what are you talking about? No, apparently we went to the moon and you have those photos. What are you talking? No, yeah, that was definitely.
That was crazy, dude. Because that means
on a side tip, he said, if we're going to continue colonizing the moon and Mars, he said that as well.
He said that?
Yes, he did.
I missed that one.
I missed that too.
He said that? I missed that.
Yeah, I believe actually he did say something about if we're going to continue to colonize or something. I mean, something to that effect. Yes, I remember.
Yeah, I got to go back to the video on that one, bro.
Well,
I got to go back to the video on that one.
Yeah, if we're going to run with the heliocentric, then you just got some insider knowledge on colonization of space, if that is the case.
Wow, dude. This is incredible, man.
Yeah,
I mean,
That was one hell of a call, Robert. I mean, that was one hell of a call because that guy. I'm not sure if that guy's going to have a job too long.
No. With him, dude, it wasn't designed to be an attack. It was designed to learn.
Oh yeah, yeah.
I was hoping that he was going to say something, where we catch him, but no, we did. I mean, yeah, he said a few things that we got him on, but that one thing I'm concentrating on now is he says that there ain't no way you're going to see a real image of the entire Earth and the sun in the same photo.
Yeah, that's why we never see him even try to attempt that, huh?
But here's what gets me, is that if what he's saying is true, that means that the photos that they've shown of the moon going in front of the Earth or whatever have you and passing in front of it, shouldn't we be seeing a shitload of light? Right?
Yeah.
We should be seeing a lot of light in the background. We don't.
Like Jeranism said, we know what the full moon looks like, so if it's lit up on the back side in between the Earth and Epic, then that should look just like a full moon does from Earth, And it wasn't. It was all gray and
yeah, dude, that's crazy, man. That's crazy.
Yeah, we should have pictures of the moon and the sun together with the Pioneer spacecraft.
Yeah, we should. Yes, absolutely, we should, but we don't.
That's crazy, dude. I think I might call this dude again. I think I may call him again, dude. I think,
especially in chat, everybody was, get him, getting all pissed and hostile and stuff. I'm like, man, that's what separates Robert from the rest of us, man.
Yeah, I didn't see the chat. I couldn't see the chat because I was paying attention to what he was saying. I mean,
they want you to jump through the phone and just hit him in the head with a golf club, you know what I mean?
We were waiting for the kill shot. We wanted to hear him bury himself live with all these witnesses.
That's great.
He exposed a couple things, and one of them was about the artist rendition of what we're looking at, and clearly admitted.
Oh yeah, we can't trust photos anymore. That's for sure.
Oh,
that's
man.
for sure. Everybody talking about the flat Earth. You cannot use another photo as proof anymore.
Never.
Yep.
You can never use a photo.
Too easy manipulate.
It literally, he just forced us all to look at the damn documented science.
Yeah. No, it was good. Like I said,
if it's not a video, if it's not a real-time video, he just confirmed to us that all the photos we've ever seen are all bullshit.
Yes. Yeah.
And
that's what he said.
Wasn't the first lady you were talking to, didn't she refer you to him? That was her photo.
Yeah, that was her boss. That's her boss.
Yeah, she was in charge of making the photos.
She's in charge of making the photos, dude. So I'm never going to use another photo again in another video, dude.
Yeah, we was already there, but yeah, I feel you.
Yeah, we just can't. We cannot use photos anymore. You can't refer to a photo as proof.
And that just shows you how little they really know about what these photos are supposed to look like, because the technology that we have could make a hell of a lot more realistic looking photo, but they just don't know what the hell it's supposed to look like.
And that's the thing. I heard someone told me, Jaron said the other day, if an amateur guy can take a regular camera and put it on a balloon and set it for automatic aperture adjustment, why the hell can't NASA do the same thing and put a camera out there and let the camera do its own adjustment?
Yeah.
They don't want to do it because they're afraid, oh man, we've been putting out these fake photos for 100 years. Oh man, we're going to be done. We're going to be done.
Yeah, it's like they can't even advance their own technology as far as pictures go because they would just, destroy their own.
From what he told me, there's 3 solar monitoring satellites out there, dude. 3. And they're all within the same range of each other doing different things.
Yeah, it was kind of funny how we spoke of, because I watched your thing on Sophie and the Hubble and everything, and Rob, that was great, by the way. The video on that, if anybody hasn't seen that, please watch that. The cold call that we did on that was awesome, and looked into it a little bit more. And he admitted as well. It's like no, it's spacecraft. Well, spacecraft could even be a very high altitude plane of some kind, and that's how they're getting it. He never once, at least during that particular part of the conversation, said satellite. It was always, it was high altitude plane or spaceship of some kind going around, and he never got like past that point. I think it was brilliant, absolutely brilliant.
Yeah, I don't know who I'm gonna call now.
Well, I'm interested to know.
Dude, I may need to take a break, man. I got a lot of reading to do, bro. I start another class next week, man. Man, oh man.
You know how they say you
Nothing.
can't see stars in space? Then how is it that we can see the fucking sun from space?
That's what, and you know what, man. That question was right on the top of my head, and I forgot to ask it too, man. I was like, man, can you tell me why it is we can see the sun but nothing else, man? Oh, I'm gonna have to call him back, man. I'm gonna have to call him back next week, bro. I'm definitely gonna have to call this dude back, man. We had a good conversation. I ain't make him mad, so I think I'm gonna have to call him back, bro. So we need, you know what? I want to get some other people up in here. I definitely don't want Flat Earth Matthew, man, because he'll probably say, hey, get off the phone, man. This dude, he talking about the Flat Earth. Yeah, nah, I'm gonna keep people out of this whole thing while I'm doing the conversation, but I gotta have somebody send me the questions to ask, and then I ask this dude, man. But yeah, that's crazy, man. That's crazy. I'm never trusting another photo. You can't. Anybody out there putting out Flat Earth videos, you cannot use photos. They're not real. That's not a real depiction of exactly what it's supposed to be. It's somebody else's idea.
Yeah.
It's someone else's idea.
Yeah, absolutely. And admittedly, with the pictures, they said no, that's an artist rendition. As soon as he said artist rendition, man, that was
composite on the NASA sites when you're looking at Hubble stuff. It's a composite of like 15, 16 different instruments to make this one. So why is it you need all that equipment to take a simple photograph?
Yeah.
Exactly.
Yeah.
Exactly. And you heard him say that they couldn't put a bigger telescope on these instruments because what would happen to it? It would melt. He said they can't put a bigger lens up on there because it would melt. No. I mean, let me correct myself. I think what he was trying to say was that if they put a bigger lens out there, these things are not designed to capture all that light from the sun.
Mask over the lens.
Can't you put a big one? And he's saying it would put out too much light. It would literally damage.
Damage goddamn day. How does it not fry?
I don't know, dude. This is crazy. Dude, let's share emails, man. Let's share questions and what we could ask these people. You guys, you saw the websites I went to, man. Just go to those websites. Think of something you can come up with. I think I'm gonna call this guy again next Monday. I think I'm gonna call him again.
I would have to say the guy was very courteous and answered.
Oh yeah, he was. Well, here's the thing, man. Everybody else out there can do these calls. You don't have to be in school, man. I mean, it's just read the documentation. Say, hey, listen, I'm reading this document. Could you? I got some questions. Could you explain some of the things I'm reading in here? And they will talk to you. Do the same thing I did. Just go to the website, call one of these people, and say, hey, can I talk to you about something?
Yeah, exactly. And the guy was pretty forthwith and very, very.
And I talked to you.
Yeah,
that's it.
Hey, Robert. I just want to say thank you before I take off, man. Appreciate it, man. It was good.
All right. Peace out, man. Take care.
See you soon, Justin.
Later, Larry.
I'm gonna put a lot of these links out there for people, man, so they can see this stuff.
Oh, hey, Chris is in here. Hey, Chris.
How you doing, guys?
What's up, Chris? Man, what happened, bro?
I was waiting for my invite, brother.
Oh, bro, I'm sorry, man.
Just hung out and listened.
Dude, this shit is crazy, man. I can't trust another photo. No way. Unless I take that photo, I'm not trusting it.
Yeah, which is kind of funny in itself, Rob, because they're doing as you know, Jake. I hate to say Flat Earth asshole because the guy's really not. I don't know why you picked that name, but Jake's channel, doing the shoot the moon thing for 3 weeks. It's today as well, and doing the whole thing. And then they came up with, well, shoot the sun thing, and I'm like, well, they're already doing it with the moon. Like, why would you have to do twice and get different cameras? I mean, taking a cell phone and trying to shoot the sun, it's going to be blinded by the the brightness of it. It's not going to work too well unless you have a certain camera and go here and get this camera. It didn't make any sense to me, and it's already underway with doing the moonshot. And I think him and he, as well as Jaron, are actually going to put together a whole topic or a whole video on it and show the results of it. Well, listen, everybody can see it from this distance. And I did this with Jake actually on Facebook. It was just off the cuff, and he's in California, I'm in New Jersey, and we had somebody in Hawaii at the same time, I think it was Tope, and somebody in Spain who saw and took the same picture as I did here on the East Coast, all at the same time, like within minutes, within 15 minutes, showed the same thing. And that's what kind of prompted him to go ahead and do this, to say, hey, look, there's no possible way on a round basketball this could ever work this way. And that's where it kind of all took off from. But I'm not sure why they're doing a second one on the sun issue thing when they already have the moon thing going on.
Here's another thing to ponder as well. You've got all these people around the earth talking about being sun gazers or sun eaters. And they wake up every morning and stare into the sun for anywhere from 10 seconds to 40 minutes. So if the human eye can withstand direct sunlight like that, how is it optical instruments cannot?
Yeah, that's a good question. I can't even look at the sun unless I got a welder's mask on or something like that, like Zen had on the one time when he did the thing with the sun, had the welder's mask, obviously to shield the brightness of it, and also.
Well, you're supposed to build up into it. You're not supposed to look at it like at noon, like early morning sunrise and then sunsets when you start out. But there's people that have been doing it for years that can go out, broad daylight and just look at the sun for a while to charge up. So if they can do that without damaging their eyes, it makes you wonder, how is it a shielded or screened camera can't do it?
Yeah, that's a great question. That's a great question.
Also, you can take acetate, like clear plastic sheets that are either colored with like reds or blues or whatever. And you can put 4 or 5 of those together and put those over your cell phone cameras and get pretty decent shots as well. Also, you can take acetate, like clear plastic sheets that are colored with like reds or blues or whatever. You can put 4 or 5 of those together and put those over your cell phone cameras and get pretty decent shots as well. Also, you can take acetate, like clear plastic sheets that are colored with like reds or blues or whatever. You can put 4 or 5 of those together and put those over your cell phone cameras and get pretty decent shots as well. Also, you can take acetate, clear plastic sheets that are colored with reds or blues or whatever. I know what's going on, man.
Brooke, we can't understand the words you're saying, buddy. We can't understand you, bud. It's Luke.
Let me drop out.
Yeah.
Oh my goodness, this is getting a little crazy. Robert, can you mute that guy or something?
I'm not talking. I dropped out. I'm on a loop. I don't know what's going on.
That's good. I don't know, man. I can hear it. Where are you? You gotta mute yourself or something.
Dude, I can't even mute him. Why can't I mute him?
No, it's Farouk. I don't know. It's your mic though.
All right, so listen, guys. Can everybody hear me?
Yeah.
Yeah, I gotta have some lunch. I got a bunch of business phone calls to make and shit like that. So this was fun, man. I really appreciate everybody being out there. I'm gonna put up the links in the description section for this, and people can enjoy doing some research, helping out. Anybody wants to compare notes with me, share any information, make any recommendations on how this can be improved, please do feel free. Email me, and let's talk. Let's talk. We can do a private hangout, or we can do a public hangout, or whatever, and just share ideas. I'd like to actually just talk private. I don't like, just talking to fucking talk on a hangout and posting it for the whole world to see.
You're right.
I ain't into that fucking drama bullshit.
Yeah, no.
Yeah, let's all get together and do private hangout or whatever, and we can share notes. You can contact me on Skype. Here's my Skype ID. My son's going crazy right now.
Yeah, it's a terrible twos, man. Terrible twos.
Yeah, terrible twos. I got to tend to him. So yeah, guys, peace out, man. Really, take good care of yourselves. My new slogan from now on is setting the truth free from a lifetime of bondage. It's not what you know, it's what you can prove.
That's right, man. Good chat, Robert. Thanks for having me, bro.
Hey, you guys take care. Chris, holla at me, man, a little bit later, bro, so we can exchange some notes and talk about some things, bro. You got my number?
Yep.
And let's just chat, all right? Give me about an hour, okay?
Yeah, no problem.
All right, brother.
Okay.
Take care, people. Peace out. Be
See you
good
guys.
to each other, and I'll post this up. You can share it with anybody you want. Take care.
Cheers.
All right, bye-bye.